Our host is going to actually be the presenter, so I will be the host for this time. And he's going to tell us all about the work we did together on entropic time schedulers and the connection between the conditional entropy and the information theory of diffusion. So the floor is yours, Diane.
Yeah, thank you. So as Lucas said, I will present our recent work on entropic time schedulers. So, yes. So quick overview. Basically, currently there is a variety of sampling schedules, and usually they're highly optimized for their task and their data set. And so in our paper, we introduced a sampling schedule that basically selects sampling points based on entropy, ensuring that each time interval contains the same amount of information. You can find our paper on arXiv. And yeah, this is our GitHub page. So this was done jointly with Luca and Florian, who are both here. Yes. Yes, so overview of the talk. I will cover briefly background on sampling with diffusion models. Then I will talk about our theory behind entropic time schedules and new quantity that we introduced called rescaled entropy. Then I will show results and discuss limitations in the future work. So I guess everyone is familiar with this, but yeah, I'll just briefly go over it. So in diffusion models, we have like a forward process, which is stochastic differential equation, and the goal is to, given a clean image, add noise, so we get some noise that we can easily sample from. And that addition of noise, that process of addition of noise, is governed by this forward stochastic differential equation. And once we want to sample an image, we start from a pure noise, usually it's Gaussian, and then we follow denoising process, which is governed by this backward stochastic differential equation. And basically, the only thing that we don't know is this score term here, like log probability. And so usually neural networks is trained to approximate this score, and then we can just plug it in and solve this backward SD and generate a clean image. So one thing that you might notice is that time is not really unique. We can choose any continuous strictly increasing function and then transform from one time axis to another time axis. And how that would look in practice is given by this image here. So you can see, so this is like three data points noised by standard like EDM process. And then we choose some function given in the standard time given by this curve here. And then we can just transform it, our SD, into an SD in this new time. And the SD will look like something like this. So why is this important? Well, so for example, for sampling, in order to solve a backward SD, we need to discretize. Yes. So we need to discretize time. And different discretization produce different step sizes along the diffusion path, and they affect quality of a generated image or get generated sample quite a lot. So there are some common schedules that are, for example, linear cosine. There's EDM one that is optimized for images for second order solvers, and there's a log space. And most of these schedules are actually linear indifferent time variable. So we can think of them as just performing a change of time variable and then discretizing equidistantly in that new time variable. However, there is no a priori canonical choice given your data set, like which one will work the best and for which solver. So how that would look in practice, like the linear the time change is something like this. You have your function, you evaluate it at your sigma time, like noise time, and then you wanna when you're sampling, you wanna sample equidistantly in your new time variable, which is given on your on your y-axis, and then you look which noise levels correspond to those times, because your neural network takes as input your noise, and then you can generate your sample. So our guiding principle in this work was the idea that in some simple case, you can actually show that optimal sampling schedule is given by this function here. And so what this tells us is that in this simple case where we look at the Gaussian data, the optimal sampling schedule for first order solver is linear under change of time variable. And also it depends on data through this variance C. So based on this, we can think of like a good sampling schedule, and some ideal properties would be that it contributes equal progress along the generative trajectory. So what that means is we would like to have some quantity that reflects how difficult generative process is, and we would like to each step basically contributes the equal amount of like difficulty. So in the end, that every step that we took contributes the same amount. And also what we saw from the previous slide is that ideally our schedule should be data dependent. So our proposal in this paper is that the good candidate is entropic time. So why entropic time? Well, so we can think of generative process as slowly uncovering more and more information about the sample that is generated. So at the beginning, it's pure noise, so we don't know. We only know basically the mean of our data distribution. But then slowly, as we continue generating a sample, we slowly denoise more and more, and we start seeing our sample. So one idea of how to define generation difficulty is information uncovered per step, like how much information we can uncover at a certain time point. And a good quantity that captures this is actually conditional entropy. So conditional entropy of x0, our sample, given xt, our noised sample or image. And so you can see here how that would look like, how entropy would look like for 3 data points shown earlier. And also in our paper, we show that actually, if you want to use entropic time, it does not depend on your parameterization at the beginning. So your arbitrariness of time does not play a role when you move to entropic time, which is something that is also desirable.
So it means that essentially you start with a time access that is completely arbitrary, just your own decision,
Yeah.
and then you do a time access that is objective. It's actually defined by the data itself.
Yeah, so
I had a question about because you showed in the last slide, you showed the optimal scheduler with the arctan.
Yeah.
Is that in any way related to entropic time, or is the point just that the optimal scheduler for the Gaussian requires the use of the variance?
So we will see later how this guided our choice for sampling schedules. So basically, a rescaled entropy was introduced because of this result. Yeah, but one of the main things that this result shows is that, yeah, basically your optimal sampling schedule should depend on data distribution somehow. And all the other schedules actually do not care about your data distribution. They're just out of the box. You get like EDM, you define your parameters, but there is nothing there.
Yeah, but the point, we will see the entropy showing up from this expression. It's just that it's not exactly entropy, is what we call rescaled entropy. It's a quantity that we are currently investigating. And it's, so entropy is there, but it's not 100% entropy. The reason is probably the fact, and Dejan will discuss it later, that it's a continuous distribution. So there isn't an entropy, there is an entropy rate. and therefore you need to have a kind of a correction term to kind of fix the divergence of the no, not the entropy, I'm sorry, in differential entropy. So you will have this divergence of the differential entropy going to zero for information theoretical basis.
Okay.
Yeah. So basically, it turns out, yes. So we have our candidate. It's conditional entropy. But the question is, how do we calculate it in practice? Like how easy it is to obtain it? And it turns out there is really nice expression for conditional entropy production. And then we can just integrate it afterwards and get our conditional entropy. So conditional entropy production is given by this expression here. But this expression here can further be like simplified in such a nice form as given by this formula here. So what we have here on the left hand side, it's conditional entropy production. On the right hand side, we have this like factor, weird looking factor here, and then mean squared error. So in our paper, we denote mean squared error by epsilon t squared. But then there's still this weird factor that might seem like what is it doing here? But it turns out that this factor is just like minus time derivative of signal to noise ratio. And actually this result is known in information theory literature by IMMSE, or like mutual information mean squared error results.
And of course, this, if you're familiar with diffusion, this would be also familiar to you in the sense that these kind of terms quite pop up often. Epsilon square is basically just the denoising score matching error up to rescaling, and which is essentially what we actually every day use for training diffusion models. So there is this strong relationship between the training loss that we're actually using and the conditional entropy rate. And then this SNR factor, sometimes, for example, you see that in diffusion papers, famously in the like Kigma paper, for example, on the use of the likelihoods. So yeah, it's we have this kind of nice kind of classical information theory results and a lot of quantity that actually people care about in the field of generative diffusion.
Yeah, so some of the connections, yeah, we noticed some nice connections. So for example, connection to the denoising score matching. In the paper where they derived the commonly used loss, they have some like leftover term, and it turns out that that term is proportional up to some constant, like up to some factors to like entropy production. And actually this expression here could be used to bound calculated entropy production, because on the right is what we estimate. And then on the left, we can see that there is correct value, and then there is this always positive value. So this tells us that entropy production that we estimate is always bigger than just correct entropy production, or equal if this is equal to 0, of course. Another connection that we notice is connection to variational lower bound from Kingma's paper, Variational Diffusion Models, where they show that as you take the number of steps to infinity, where you go from discrete to continuous space, of from discrete to continuous time, you get that the variational lower bound is given by this expression here. And you can see that it is really closely connected to conditional entropy of your data given like fully noised image. Yeah, I mean there is this factor 1/2, but it's just a constant, right? So they're pretty much the same.
Is x1 like t equals to 1? So
x1 is so here time 1 represents like Gaussian noise, basically. Yes, so you can actually think of this as just entropy of your of your data, right? Because like x1 is not really contributing a lot to x0. So
yeah, except it shouldn't contribute at all, right?
yeah. Like in the perfect world, it's not contributing at all. So it's just like entropy of your data x0. Yeah. So yeah, I mean, this gave us some incentives to believe that entropy is the correct quantity to use. However, conditional entropy blows up for continuous data because that there's a difference between like entropy for discrete data and like differential entropy, right, for continuous data. And it turns out, I mean, to specify like a real number, you need infinite amount of information. So that's an idea why conditional entropy actually blows up. And so in order to battle with that infinity, that singularity, we introduce a rescaled entropy by this expression here. So this is connected to signal to noise ratio as we saw before. But so you might ask, like, what is the meaning of this rescaled entropy, and why did we introduce it besides just being like randomly, oh, it blows up, so let's just introduce something new. But it turns out that the result that I showed before, like the optimal result for a Gaussian case, it turns out that rescaled entropy gives you exactly that schedule. So we were guided by that result to define actually rescaled entropy, and then later we
By the way, so if for people watching, if you know how to interpret this quantity from the point of view of either information theory or statistical physics, just drop me an email because I still don't, and it just stresses me out. And I think once we will be able to interpret this quantity in a more general way, then we will be able to actually properly characterize the theory of optimality for scheduling for arbitrary distributions.
yeah.
Because it's probably manifold dependent. It probably depends on the support of the manifold and the structure of the data. So we don't expect this to be optimal in general for non-Gaussian data, but to be a close approximation. And I feel that once we understand this object information theoretically, then we will actually know what the true optimal sampling distribution is in the general case.
Yeah, exactly. So we feel like this rescaled entropy is good for directions or like on your manifold that are actually like extended, right? And the dimensions and directions where data is actually singular, like just discrete data. I mean, in that case, conditional entropy is well defined. So we believe that conditional entropy is better suited for those. So one kind of connection. I don't know how to call it, but so in stochastic thermodynamics, there is some type of work defined by. So they have their definition of total like entropy production, and then they multiply it by temperature and then integrate it, and they call it I think dissipated work. I'm not expert in stochastic thermodynamics, but which resembles our equation for rescaled entropy, and there it can be shown that actually it bounds Wasserstein 2 distance between your clean data distribution and your noise.
So, but what is T?
What is T?
Yeah.
T is sometime like I mean,
big T, big T.
Oh, big T is temperature.
So, but in diffusion, temperature is more sigma squared than sigma, right? So that.
Oh, sorry. Yeah. So I mean, it's still unclear because I think in one paper they for this temperature they used like noise term in SD, noise term squared.
Yeah.
And then when you look at noise term squared, it's exactly like for EDM SD, it's exactly sigma T.
Yeah, but that's You're saying instantaneous noise.
Yeah. So
That's
I mean,
not temperature too, right? At least in diffusion, that is not what you would call temperature. But I guess in that context of stochastic, because the instantaneous noise does not give the scale entropy formula, right? It give it by coincidence in a VM.
no.
But that's a coincidence. It wouldn't give you the correct. It wouldn't suppress the divergence in many scenarios. I mean, the obvious case, right? If you have a Brownian motion, then the instantaneous noise is constant. So then you just get the standard conditional entropy there.
Yeah, yeah, and also then your formula is no longer like invariant under time reparameterization as well. So.
Yeah. But if you interpret it as temperature in diffusion, then it gets close. But then it would suggest that it's more sigma squared than sigma.
Yeah.
But I mean, this is food for thought, and we don't really understand this, but this is just good.
Yeah, no, I just thought like it's interesting that it resembles kind of like it's not out of.
So I had a question about the rescale entropy. So you're weighting the entropy rate by the noise.
Yeah.
So that because the entropy rate unweighted goes to infinity.
Yes.
Okay. But you said this was related to the arctime schedule, the optimal scheduler.
Yes.
But the optimal scheduler, at least from what I'm looking at the formula, it seems to say, given some time schedule, it has to apply, it has to withhold that condition, but it's not obvious how that relates to rescaling.
Well, you just need to take the derivative, right? So you take the derivative of the. Do you have a slide with the derivation?
No, like of the equation, no. I mean, it's in our paper, so in appendix, yeah. The appendix.
Maybe you can pull it so you can show because I mean, it's not obvious from the formula, right? So it's good.
Yeah, yeah. So let me.
Because at least from just the formula, it's not obvious it has to do with it.
Yeah, you need to take the derivative and then you look.
Okay.
And then you need to compute what is the entropy rate for a Gaussian.
Given that scheduler. Or,
Yeah. So basically, yeah. So there is this result, right? This is optimal in for certain solver, right? And then then we define rescaled entropy, and then appendix E. Yeah, so you can just go through like through the motion, right? Just calculate your conditional entropy production, which is and multiply it. So we know how to express it, right? Like I showed it on like previous slides, and then you multiply it by sigma tau, and you get this expression here. And now the thing is, you know that Gaussian with other Gaussian noise is still Gaussian, so you can easily calculate this score and norm squared of it. Right? Yeah. So there is this formula here. And basically, when you do that, and I mean, this is also like you know how to express all the terms so because like this is EDM stochastic differential equation, so you know this is just. Oh, this is a mistake. Nice. So this should be tau. Yeah. Good. But I mean, the preprint will be updated with like NeurIPS versions.
Okay, you can see that the entropy rate is, if you integrate that rational function, you will get the arctime. So if you start with the definition of rescaled entropy and you compute it for Gaussian, you will get the optimal result.
Okay.
It's our opinion that this is not a coincidence, that there is something fundamentally entropic in the optimal solution. It's just that we don't fully understand the reason of the rescale. And how it will apply to situation, for example. Like the interesting question, for example, okay, it should change the support of the data. So let's say that instead of having a Gaussian, you have a manifold supported Gaussian. How does it change the picture? And essentially it changes a lot the divergent structure of and the extreme is a Gaussian that shrinks to a single point. And then we can consider the mixture. There we have kind of good experimental support that the entropy itself without any rescaling is near optimal. So it's essentially this rescaling is due to the divergence. When you have things shrinking to a point, there is no divergence anymore. And now the fact that there are a lot of intermediate cases in which there is divergence in some range and non-divergence in the other. There is a bit of the need here for a kind of a full theory of optimality of how these kind of things relate to the. Yeah.
But you say shrinking to zero. Do you mean at time equals zero that it's
yeah, time equals to zero.
So it's like in language that would be the case.
In language, for example, yes. If you have discrete symbol, it would be the case. So there we conjecture that you should use actually the conditional entropy. We have quite strong support both from sampling and training. That seems to be actually a very good choice. We don't have a full mathematical theory of that. Yeah, there is a lot to be understood here, and I think that those are things that can be understood, and especially for people with a bit of ability and sophistication for abstract math and physics. Yeah.
Yeah. So. Yes, so we also tried to introduce spectral rescaled entropy, just because, as we have seen, that conditional entropy depends only on norm squared. So that means that we could we can just split it into any orthonormal basis and look for each basis element, right? Like the value of it. Then, I mean, in the end, this is just summation over all those orthonormal bases. So we just said, like, okay, what happens if we look at Fourier basis, and then instead of just summing it up, we say that each Fourier basis it has, like, we normalize it to 1, and then we reweight it by how much that Fourier basis is present in the data set. So trying to rescale it with respect to, like, spectral properties of the data set.
So the intuition here is that essentially the information theory essentially does not care about magnitude that much. You know, the example I like to make is that if you have a book with written in large font, or the same book written in small fonts, that's the same information content. You know, as far as you have the same number of characters. Now, that in an image, there could be low frequency modes that for the human eyes would be basically indistinguishable, but still they convey a lot of information because, again, entropy does not care about magnitude. Differential entropy cares a bit about magnitude, but only logarithmically. So this is the idea that essentially there are components of the image that contain a lot of information, but we don't even see, or we don't see that much, and therefore you can rescale them based on the magnitude itself to make the scaling on the magnitude linear instead of logarithmic. This is it's an objection that you can definitely get from people used to computer vision. In fact, I was talking to Sander Tillman, and he's exactly saying, okay, I felt that maybe that wasn't the right quantity for images because of this reason, because a lot of information is not really visible. I mean, what it turns out, at least from our analysis, is that actually the straight conditional entropy works well. And yeah, as Diane will show you, just the rescaling helps a bit, and I'm sure you can get better results with rescaling. We didn't do too much effort to rescale in the optimal way. If you really want to optimize on your data, you can calibrate the rescaling and probably get better performance. That seems to be the case. We are, especially the Jan is really a physics purist, and it does not like it to introduce extra parameters in its model. So.
Yeah. Yeah, but I mean, we can see the symbols case changes it a bit, but not a lot. But it turns out that this bit is quite a lot. Yeah, and so on this plot here, you can see the difference between, like, EDM sampling schedule with respect to, like, rescaled or spectral rescale entropy, and also, like, you can see how different radial frequencies differ. So you can see that, for example, the frequency 00, which is basically all the pixels have the same, right? Like, it's a constant. We can see that it takes quite a lot of time to noise it, which makes sense, right? Like, it takes a lot of time to lose information because the information is everywhere. Like, and then for higher frequencies that oscillate a lot, we lose information about them quite quickly. I mean, this is intuition that people had, and I mean,
yeah.
But
It's a nice formalization of this intuition that higher frequency components emerge later in diffusion. Here now you can see that clearly from the entropy curve. And now the thing to keep in mind that there is nothing to do in itself to the frequency. It has to do with the variance, with the amplitude of the frequency components in the data. You see, this sorting comes from the fact that in real images, high frequency components have less variance in the sense of PCA than low frequency components, and therefore they will emerge later. Okay, but if you make up a data set in which high frequency components have higher variance, so they dominate the image, then you will see the opposite. Okay, so it's not the general rule of information theory. Information theory only care about how much that component is present in the data, and the fact that low frequency components are not very much, because the Jan set is global, and that is true that the zero of components is global, but the fact is that all components are global. Those are Fourier components, so they're all global oscillation. The fact is that a lot of these global oscillations have very little variability in the data, and therefore they are easily overwhelmed by the noise because their amplitude is very low. Okay.
I have a question.
yeah.
I still don't really get how you get this plot. So you took conditional entropy from a pre-trained model, or this is from the Gaussian case? Or no, it's not the Gaussian case.
So this was so I think this was for ImageNet 64. So,
and then you get the and how do you get the rest of the plot for?
So basically, you look at this, right? And the thing is, this is basically when you write it down, this is just summing your. So you look at the first component of this vector, of this difference, right? And square it, and then plus the second component squared, plus third component squared, right? And the thing is, you can if you change your orthonormal basis, this quantity will stay the same because like norm squared is will not change. So if you do that, you can then look at specifically for like new basis, and then you can again look at the first element of this vector in new basis, the second element of this vector in new basis, and then by looking at only those, you can you can get all the like frequencies.
So can you say that this is kind of like a way to analyze maybe the encoding the spectrum of the data or not?
So I mean, this does give us information about, as Lucas said, like how much they like their presence, like how much they differ, like variance of them in the data, right? In your data set.
Yeah.
But in order to get like magnitude, you need to take your data set and like get like a spectral decomposition and see how much certain frequency is present.
Yeah, okay, that makes sense. Thanks.
Yeah, because like if all of them had like high magnitude for one frequency, but it was high magnitude, the same value for all of them, then I mean there wouldn't be any entropy there, but magnitude would be much higher, right? So like magnitude and this plot are not really connected. This is, as Lucas said, more about like uncertainty, like how much uncertain I am about certain frequencies.
This plot, maybe if we go back a second, this plot is why I cringe a bit when people talk about just the SNR of a diffusion process without mentioning the data, because the SNR depends by the signal. And you can, as you can see, the SNR, this is essentially as an SNR curve component by component. And you can see that different components have very different SNR. So there isn't a single SNR during diffusion because you have highly dimensional signals, and some components will have much higher SNR than the other. So entropy try to average over all these things, and that's why you get the square norm that is essentially just averaging over all tests and error, all of them. You could also try to optimize some components specifically or reweighted in a specific way that you are interested. But essentially, there isn't a single SNR because the different components of your data have different variants. So that the signal, the noise part is fixed, but the signal part is not fixed.
I had a question about the spectral entropy, because in the last slide you have for the rescaled entropy you weighted by the noise, but for the spectral rescaled entropy, would you then have another weighting factor based on the frequency of the frequency, how common a specific component is?
Yeah, magnitude of that frequency for the data set. Yeah.
And
okay. So like the total amplitude in the data set.
And that then determines your weighting factor.
Yeah. So if something is you weigh the curve more.
Well, how are you weighing it specifically?
Linearly.
Okay.
You just multiply it, right? Like, because they're all, I give them the same importance, or I normalize each frequency to 1 like this, and then I multiply it by that weighting factor. So it just it's assigned weighting based on like how much it is present in the data set. So yeah, if it's, and usually images have like quite standard like spectral like matrices. So you usually like there is bright spot in the middle and then slowly decaying, or like slowly is questionable, but yeah.
So, but should I interpret this plot as I set the weight for one component to 1 and then all the other weights are 0? Or
Is it? No. So okay, yeah. So these like not dashed things are just one component. Yes.
okay.
Yeah. So they're just representing one. So this is like frequency 0, 0, or basically just a constant function. Yeah. But then in order to obtain this red dash thing is I okay, yeah, great. So I reweight all of them, like all of these non-dashed curves. I reweight with their amplitudes, and then I get like this red curve, dashed curve. Yeah.
Okay.
Actually, yeah. Any other questions? Okay, yeah. So results, yeah. So as we already discussed, our suspicion is that rescaled entropy works for continuous data where variance is high, where like our data is actually extending in those like directions, and that entropy, conditional entropy, is a good candidate for like discrete data, or data where or dimensions where data is kind of discrete. So we tested it on like toy example, on like 1D example. So how it performs, how different schedules perform for like discrete data, and so mixture of data points and mixture of Gaussians. And what we can see is that actually entropic time outperforms rescaled entropic time and standard time by a, quite a big margin, I would say, like several orders of magnitude. So this is KL divergence, what we are measuring. And then for Gaussians, we see that rescaled entropy outperforms other schedules that we looked at. We looked at also at some other schedules, but I mean, we thought that representing only 3 curves is enough. Like it would probably get overcrowded with more curves. But in general, this is the trend that we observe. Like entropic time, in discrete case, outperforms everything, and then in continuous case, rescaled entropic time performs better. But you can see that as you increase number of generative steps, they're actually converging. I mean, in the end, they should all converge, right? Like if you take like 1,000 generative steps, yes.
Yeah. In this case, you mean standard time just linearly spaced times, or are you comparing also with the scheduler from EDM paper?
No, so this is just linear, but we also compared like I also looked at I think log linear, and like I looked at some other common scales. So not all of them, but I can look it up. But like in general, like they were all somewhere, like they were not beating the best models, the best schedules. Like they were somewhere in between.
Mm.
So yeah, and especially for discrete data points, nothing was comparable to entropic time. And then I mean here, as you increase dimensions, and you get like high dimensional probability, so things probably behave different. I mean, they do behave a bit differently than in 1D case. So this was just to get an intuition how things work. And then in higher dimensional space, we used we used EDM like trained models, and we tested our method on ImageNet 64, ImageNet 512, and like Cipher10 data sets that were available in that models, EDM models that were available for data sets, those data sets. Yeah. So you can see comparison between like EDM schedule. This is ImageNet. So you can see the difference between EDM schedule and rescale entropic schedule. So there are some differences. And I mean, the biggest difference that I see is actually lighting, like brightness. EDM schedule is quite bright, while the rescale entropy gives a bit like less brightness, and it looks to me more natural.
I mean, it's also sharper, right? You can see that the rescale entropy versions are quite sharper than
Yeah.
a bit blurry EDM ones.
What's on the x-axis?
Hmm?
What's on the x-axis?
Oh yeah, so I didn't. Yeah, so the thing is, this is how they differ with different number of function evaluations. So this was generated using deterministic DDIM, and so I used it and same like initial noise, and then I looked for like 8 function evaluations, 16, 32, and 64. So I mean, the idea is as I increase number of function evaluations, they should start converging on the same image. But still, like 64 is not a lot, so schedules still play a role in it, and we can see like some of the differences. Yeah, I mean, like you can see like the eyes and nose here compared to here. Yeah. So here as well, like you can see that in general, like the brightness, like green, and this greenness of this worm, I guess, is much higher than here. Like this looks a bit more, and then you can see like the differences in the images. So, and also details. Like I would say like rescale entropy gives more details. Like you can see more details here, more details on the dog.
Be sure to put this image is very nice. Put it on the poster. I mean,
Yeah.
poster. It shouldn't just be math. At the conference, it's just good to get people attention.
And for this example, how many steps do you use?
So this is again like 8, 16, 32, and 64.
64.
Yeah. So I mean, for 64 steps, it looks like quite a big difference, right? Like there is a leash here, and then this is like, yeah, there is no leash here. Yeah, 2 worms. Like here, you have this thing here that I mean, I'm quite unsure what this thing is representing, but you can see that there is nothing here and something here. Yeah.
What is funny is that the EDM looks like it's missing the small details, no? And maybe due to the log normal that
Yeah,
it's not I'm not quite sure if for sampling maybe it sample less close to small sigmas.
So I mean, if you go here, you can see that actually, to some extent, like rescale entropy is more aligned with this like shape of these curves, and like especially shape of higher frequency curves compared to like lower frequency ones.
Yeah.
So maybe somehow, yeah, it affects that, because like higher frequencies are actually there for details, right? So maybe it pays more attention to details, and that's why you have better details on like rescale entropy compared to EDM.
Exactly, yeah, because this image looks pretty cool in terms of those levels of differences between EDM and rescale entropy.
Yeah, I mean, EDM looks like from the beginning it knows what it wants and it's just generating that thing, but like quite blurry, and like, results are not that great. Like it knows it wants something to be here all the time, like, but it's just weird. And like this dog is always looking in the same direction, while here we start differently and then slowly refine, but then like immediately we have a leash while we don't have anything here. Like it's quite interesting. Like variation here is.
I had a question about the differences between the curve in EDM and rescale entropy.
Like
So
this.
yeah, so for close to the n, closer to time equals to 0,
Yeah.
EDM, the curve for EDM is higher than
Yeah.
for rescaled.
Yeah.
So how should you interpret that then? So does that mean it's giving more focus to lower frequencies or less focus, or?
So the thing is, yeah. So you can view this like, you easiest way to view it is like looking at like derivatives, and when like derivatives of your curve are highest, you're putting most emphasis on those, because like in the end you wanna sample equidistantly on like y-axis, so you just look at like 5 steps would be like 0, 8, 0, 60. So you can see that, yes. So for really small times, you would sample closer to 0 than you would get with rescaled entropy. So you are right that it should like pay more attention. But I mean, again, it's you can see that highest derivative is probably here, so it's paying way more attention to like.
Also, the very low, the details we're talking about are not at the lowest noise
Yeah,
level, because
yeah.
at the lowest noise levels is really kind of sensory fine tuning, and this kind of details live more at intermediate noise levels.
And for are there qualitative differences whether you use second order, first order, deterministic, or stochastic?
So for first order, it does not make so these are all like stochastic deterministic VMs, so they're first order, and we can see quite consistently that, okay, like there is a small difference between like spectrally scaled entropy and rescaled entropy, which in some cases it could just be like just like random noise, so they're basically the same, or yeah, or sometimes they're like slightly better, but I mean it's yeah. So the thing is, and the thing is, spectral or scaled entropy is only available for images, and rescaled entropy is available for any type of.
Yeah, but just keep in mind that we didn't play around with the scaling at all. We just used a simple formula. You can apply the power or nonlinear function on the mixing coefficients if you really want to optimize there, and there is no reason to believe that this is the best you can do. So if you really want to optimize for FID, you say, I don't know, magnitude times rho, when rho is a power, and you kind of optimize power, and probably you can get better FID. It would be strange if the linear way is the optimal.
Yeah, I guess like if you wanted, like if you would need more knowledge about your data set, right? Like if you wanted to optimize your entropic schedules for like your data. So like you would need like expert knowing that like certain frequencies are more important or.
Oh, you brute force it. You can just have a parameterized version of the and like most people do.
But I mean, we don't know what is the best orthonormal basis for like proteins or something like that, right?
No, this is mostly where there is an obvious linear basis, and another obvious linear basis that you can use, because the problem are if they are discrete, it's quite intrinsically non-linear, and then this another problem. That's but there we know that actually entropy itself is probably close to the best thing you can do, so that you have no issue at all.
Yeah. So in general, for first order solvers, we see like quite consistent improvement, as you can see for a core. And even for ImageNet, which is done in latent space, so we don't really have access to spectral, or I mean, it's questionable how much spectral information is preserved by that like transformation into latent space. But we can still see that rescaled entropy is outperforming. I'm sorry, like outperforming EDM schedule consistently in both like FID and FDD. Although like for FDD, you can see that they can get close for this like small model, but I mean, yeah, in general. And especially like stochastic DDIM, I'm not sure which one, but like I think for stochastic DDIM, we were able to beat like second order result for FDD. Some of these is better than. Again, you can find it in the paper. Yeah.
Yeah, we mentioned like second order is the main limitation that we'll discuss later on. The sense that for a low number of function evaluation, with the state of the art are second order solvers like Coin. And there we don't think that the entropy is, at least the kind of entropy we're currently studying, is the complete right answer.
Yeah. So when we go, for example, all the way here, so we are trying to capture like generation difficulty, and for like first order solvers, you can think of it like if I'm trying to denoise from one time step to another, I'm basically using information available here to go to here. But like with higher order solvers, they look ahead. So like intuitive reason one might give is like higher order solvers are actually not respecting our like information transfer. So it looks a bit ahead and then like infers how to move. So one reason why higher order solvers do not perform that well when using conditional entropy. So we would need some different notion of information transfer for like higher order solvers. Yeah. So that's the biggest limitation of our work, like second order solvers or higher order solvers. And also like even though we tested like our method, we tested mostly on images and like on like toy data sets. So one thing in the future would be nice to test on some different data sets, some different modalities. So like this, going into more discrete data, or just seeing how it performs. But we are currently working on that. So to summarize what we did in our paper, we introduced entropic time, and we argue that it provides a natural time parameter for diffusion processes. Since time parameter is not really unique and well defined, so you can choose whatever you want, and we are saying probably you should use entropy or rescaled entropy, because like conditional entropy blows up for continuous data. We suggest the principal sampling schedule that depends on your data set. And we notice that it connects naturally to several quantities that show up throughout the diffusion literature, one of them being continuous time variational objective. And so interesting future directions, or I mean current directions, I can say, is entropy might be used to guide the training or distillation of diffusion models. Because as we said, like entropy is just telling you how to go from like arbitrary time to like unique entropic time, and then again, like entropy might be a good candidate to represent how like difficulty of training, or it could be used for distillation. And so the thing that is left to be done that is quite unclear right now is to develop entropic analogs for higher order solvers, specifically second order solvers, because they're commonly used in practice, and also to understand better rescaled entropy. So with that, we can move to discussion. Yeah. Yes. Thank you. Gabriel had a question, right?
Oh yeah, thanks for the nice presentation. Do you think that, for example, the impact of this sort of understanding of time reparameterization via conditional entropy can have like a similar impact to, I don't know, for example, now with log SNR, or just reparameterizing the time with sigma in the community? Do you think so, or do you see some limitations that may block that?
So I mean, so problem with using entropic time, like you use sigma or signal to noise ratio or log SNR, is all of those quantities have nice expressions. So like you're in control of them. Like you define your sigma, and then or your like log SNR has nice expression in terms of sigma. So basically, you're just looking at sigma in the end. Like all of them are connected to sigma. Well, entropy depends on your data set, and it's quite unclear how to like have it in many expressions, right? Like because. So I mean, I would say it's not as easy. Like it's not as nice quantity to have like in your formulas. Like you have sigma or log SNR, but I think where it's most useful is, yeah. So basically, this is the thing. Like first of all, you don't have access to entropy at the beginning. So when you're training your model at the beginning, it has to take these sigmas or log SNRs or something, because once you're setting up your diffusion problem, you're setting up your sigma basically, right? While you're not setting up your entropy, so you don't know what it will be. So basically, what your neural network is taking in is this sigma, and then later you can estimate entropy. So entropy, I feel like, is good for sampling, because then you can easily just go back to sigmas and then use it for sampling or for training as well, because or distillation, where you already have like a trained model and then you distill it again, like you can easily estimate entropy in that case. So I don't think it's as nice as sigma, because it takes more effort to get it, and it's estimated, while sigma is just given by like your statement of the stochastic differential equation, right? Was that
yeah, that's one of the questions, but I think that's also the problem. Not you need to define how you define sigma, which comes with a prior. Yeah, but I mean, like I think then comes with a similar problem, no? That you need to get an estimate. So I think that is good for sampling. The other question I wanted to ask you is that, because it's indeed that then you kind of have defined the boundaries, right? So this parameterization is kind of dependent on the initial, for example, time zero and time end. Do you think that we could possibly use this conditional entropy or something in an information guided way to define the optimal boundaries. So
I mean, definitely you can see, for example, like if you look at entropy, so let's say instead of 80 you use 2000, like your sigma max is 2000, right? Like using entropy, you would see that most of like entropy wouldn't increase after this point; it would just plateau, and you would be able to see that like there is no really need to go to like that high sigma max, right? So it could be used to set up the highest or to gauge where to put like your highest sigma max, right? Like from where to start your generation process. I mean, regarding the end, like it should be 0 or like epsilon close to 0, right?
yeah, but what I mean is that by design for computing the conditional entropy, you need to specify the boundaries, right? For example, to do the mapping from 0 to 1 to the corresponding kind of like space between sigma min to sigma max. So that's I was thinking if we could, so because by design you need to have that inverse mapping, right? From 0 equals to sigma min or 1 equals to sigma max.
Yeah.
But it may be the case that, for example, I don't know, so imagine that you're training a two-dimensional two example, but then you set sigma max 80, which is not really the case. And probably you could use conditional entropy to just set up that the optimal maximum noise level is, let's say, maybe 1, and the minimum is something different. Do you think that is possible, or maybe this is the limitation?
So the thing is, setting your entropy to start at 0, or like your function starts at 0, doesn't change anything. Like we have like one sentence in our paper saying that you can choose. So one of these endpoints is free parameter. You can choose it wherever you want, and you can just set it to be 0. And then whether this is 1 or anything else, you can multiply it by any function. Like you can see that even if I multiply this by 10, like equidistant steps wouldn't change. So if you say now, like you have this, and you say, okay, now I want to actually start my generation process from sigma 40 instead of sigma 80. What you would do, you wouldn't have to like recalculate anything again. You can just look at sigma 40 and then do like equidistant step from there. Okay, so this is quite steep, but like let's say sigma 10. So you would start from like 0.9 and then choose like 5 steps that are equidistant between 0 and 0.9, right?
Right. Perhaps, maybe, yeah.
So
I mean,
find that the boundary can be high, but time, when you go entropic time does not flow there. So the fact that you can have 1000, but since if there is no entropy production, once you go to entropic time, that doesn't mean anything. It's very close. 1000 is very close to 1 because you're measuring time as entropy rate, you know?
Yeah.
So it doesn't actually matter that much at the end of the day, up to the fact that, of course, you need to compute the first curve and discretize. So if you want to do things, in a nice way, you start with high bounds and high discretization. You compute the entropy curve, then you kind of rework time based on entropy, and then you can kind of zoom in if you want, and you can get kind of an optimized curve. I mean, usually it's not really worth to get to that level of precision, because that is needed if you're really entirely off at the beginning. But
I mean, one of the reasons that I was asking this question is because, for example, if you look at the design choices from EDM paper, one of the improvements, I think so, is because, for example, compared to the first sigma min on some paper, they set sigma min to be 0.02. But then in their paper on EDM, they put 0.002, right? So I thought that there might be a connection between this idea of continuous.
Sigma min, you need to be very careful too, because sigma min, usually the optimum, it depends. In images, the optimum will be 0, because there is entropy throughout.
Yeah, exactly.
So it's not, that is, in discrete data, that's different. If you have discrete embedded data, that's different because there is effectively a cutoff of entropy production after which nothing happens. So if you look at the curve, one of the first curve, right, with deltas. If you maybe go to the figure with here. So you see that at some point the entropy rate essentially goes to zero. Essentially, entropy completely flattens out, because once you are within the basin of attraction of a single embedding, times doesn't flow anymore. So in that case, is indeed something that you could optimize. If actually you should not. In practice, you don't need to optimize if you go to entropy time, right? Because essentially time is not flowing there. So it's less important what you think, but effectively entropic times tell you, and this is why this works so well in discrete data, it tells you that don't waste function evaluations in places where nothing is happening, because there is, at low noise level, essentially nothing is happening. Again, I do feel that a lot of this talk about language diffusion, continuous language diffusion not working, come from the fact of people just dropping image calibrated diffusion models on embedding, and then wasting 50% of their function evaluations on a zone that is completely irrelevant. And then you say, oh, well, we get 50% reduction of efficiency. That's bad. And I'm not saying that is 100% of the story, but I do think that the literature that moved towards optimizing this, like famously, like Sander Tillman paper on that actually did some form of entropic scheduling for language case, that didn't really get mainstream. So a lot of people trying it are not calibrating their schedulers particularly well. Some papers now are coming out reintroducing this approach, of course. Like, for example, I think in the recent Candy paper about hybrid diffusion, they used this alternative method. I don't know how much is related to entropy, but it seems quite connected for rescheduling. But my point is that if you want to work on diffusion for discrete tokens, you really need to take this kind of aspects into account. Otherwise, you're just wasting a lot of function evaluations. And if you waste a lot of function evaluation and training points for training a language model, you will see worse scaling results.
Yeah, that's something nice. I think indeed you can get somehow for free the boundaries. I'm not quite sure, but I think so. Yeah. I think that's something nice to have.
Yeah, you should just, in general, you can always use it just to gauge your sigma max, whether it's just overshooting.
Yeah, because I guess in your experiments, you did not compare that point, but I think that's somehow not clear design choice, right? And as Luca mentioned, when you move to maybe discrete or other data type, then you don't really know what is the optimal boundary, and then you again need to do the experiments until you find which one is the best. But probably you use conditional entropy, you can get those plateau regions, and then you choose the boundaries.
So another thing, maybe related a bit of our symmetry breaking work, Gabriel, is that one of the points that we made there, then other people made it afterwards, is that essentially for the first stages of diffusion, the process is essentially Gaussian, so just learning the mean and the covariant structure of the data. And that is learning, but it's learning that doesn't need a diffusion model. You can simply compute, you can simply pre-estimate that structure in pre-estimate that structure from the data, like we did in our symmetry breaking paper, and then you can use this initializer. We need to be careful. That would suggest that maybe in some situation, maybe you don't want to use the full entropy rate, because that will also take into account the Gaussian entropy, which is a bit trivial. And maybe you want to use, for example, some KL rate with respect of a Gaussian that has the same moments of your data, because that will kind of remove the easy part, which you can reintroduce by initializing, which just means you just, instead of sampling from white noise, you sample from the correct covariant structure.
Exactly.
So, that could be an interesting direction for future research. I know that Florian have been experimenting with this kind of ideas.
Also one thing, like in Kong's paper, there is so he looks at something similar, like and then he has some curves. He says, like, okay, so if curve obtained using training score is above curve obtained using Gaussian, like the behavior of Gaussian, that matches like the data. Then you can just use Gaussian because like it will perform better. I cannot remember recall the exact argument, but like basically you can get two curves. You can see whether your trained model is below or above the Gaussian curve. If it's above Gaussian curve, they say, oh, you can then just use Gaussian in those time intervals, and you should be fine. Yeah, but we will hear more about it probably in 2 weeks. So that...
I mean, the problem, I guess, that the Gaussian is time dependent, right? Not for large T, but for non T, yes, you have essentially you're Gaussianized, but the covariance structure is time dependent. It's not, I'm sorry, not time dependent. So it's location dependent, it's X dependent. So it's not, you don't necessarily have that available because it's about the local linearization structure of your data.
No, they didn't use they use Gaussian as pro marginal at PT, like at time t. Like they said they use Gaussian score, basically, score of a Gaussian distribution.
Covariance, you need the covariance structure to compute it, right?
But you don't need covariance structure of x0 given xt. Like they were not looking at that. They were just looking at Gaussian with the so you just need the variance of your data set. And then you have Gaussian at any time point t, right?
Yeah, but that's a non-trivial covariance due to the data. So you need to estimate that covariance if you want to use it.
Yeah, but I mean, if you just assume you have a bounded, and then you say it's 1, and then I mean, to some you're making some approximations, but still, if your trained score is higher than that, you can use that Gaussian.
Yeah, but remember that Gaussian does not exist for low time, because for low time, the whole distribution is far away from being Gaussian, and different points will have very different linearization. So it will be locally Gaussian, but if you just compute the global moments, you can get a complete mismatch from the local moments. Just imagine that you have a data set with a kind of two straight lines, right? One vertical and one horizontal. One is a lot of variance in one direction, and one is a lot of variance in the other. If you average, if you just look at the covariance structure, you would see a lot of variance in both directions. But the denoising, the optimal denoiser cares about the local variance. So the variance of the linearization, not the global variance. So under the assumption that the linearizations is kind of, let's say, proportional to the global structure, then yes. But if it's not the case, then you get a big mismatch. So you need to meet some extra assumption there.
No, I mean, I think they're still saying I mean, if your model gives worse curve at that interval, you should still use Gaussian. But I mean, the question is whether your model is giving worse curve. Like if it's trained model, probably in the case that you just mentioned, wouldn't give the worst curve.
Yeah,
but I mean, again, I cannot remember exactly what they did, but I know that using that curve, they said oh, we can even look at different models, different trained models, and then based on that say okay, this model performs better in this region, this model performs better in that region. So just make a Frankenstein model. And then generally,
it reminds me of the edge of memorization paper. Of course, the Goldberg work was quite different, but they have a similar kind of crossing of curves. That is the main criterion, which again I discussed a bit with the authors, and it seems that it can be formulated quite nicely in terms of entropy rates. So that's also a nice connection.
Yeah. Florian has a question.
Yeah, this is now a bit past the point of discussion, but I've been wondering if you've looked into subsets of the data. So I could imagine that these entropic curves look different once you can actually condition.
Oh, you mean like classes?
Yeah, exactly, classes. So for class-specific generation, I would expect there to be different optimal schedulers.
Yeah, I haven't looked into it, so I'm not really sure. But I guess they should be different, right? So I'm not. But I cannot really,
Yeah, okay.
I cannot really comment more about it because I haven't really looked into it. But I guess it should be different. Yeah, I don't.
But why would they be different?
I mean, because you have different frequencies present in different classes, right? Like at different magnitudes. So entropy production is then naturally different because of that.
Yeah, I mean, you can imagine, I don't know, like if you have images of, I don't know, like airplanes, the background will always be like blue, or maybe, I mean, maybe that's not, maybe there is like cloudy. I mean, yeah, but like you can have like different, like, so backgrounds of for airplanes, it might have different structure than just like backgrounds of some other class that is always on grass. So there like you have less variance, right? If you know your background, then you have less variance in your, like, less information to be extracted.
So that would be you have less variance in the lower frequencies. If we're talking about background.
Lower frequencies. Yeah, but I mean, so but if you know that most of your image is just green, then it's not just. Then it's also like, yeah, lower frequency. Yeah, you're right. Yeah.
Because I guess there's also a question for Florian. Would the idea be that if you have an image that has a lot of different backgrounds, then you would expect its conditional entropy rate to be biased towards lower frequencies, to spend more time on lower frequencies?
It depends on the frequency content of the backgrounds. You cannot really. I mean, the background can be smooth, or it can be.
Yeah.
I think, honestly, I do think that if you think too much about frequency, you get confused, because it's really not about frequencies. It's about components of the data and the amplitudes of that components, and it is true that on average, in images, you will get that the variance of the components will scale with the frequency, but don't get conceptually confused to think that it is fundamentally about the frequency, because it's not. It's about what is in your data. If your background are chessboards, if you're taking a data set of chessboards, there will be a peak in the spectrum corresponding to the frequency of the grid. Yes. Then the ground state of the highest variance will be not zero, but it will be corresponding with the grid. So you need to be careful. It's really about how much that specific frequency components, or the specific linear components, or PCA components, has variability in the data.
So I mean, like in that sense, you could probably squeeze out a bit more of this approach, even if you were able to. I mean, it's practically probably infeasible, but if you're interested in class conditional generation, to then compute these curves per class, and or even like squeeze somewhere like a network into the pipeline, then can maybe estimate them on a per class basis, right? Because then you will most likely get better image quality in the end.
Yeah, no, it's not unfeasible at all. I mean, for a small, I mean, for stuff like ImageNet, you can easily do it. For diffusion, yes. I mean, you don't want to generate. You need to generate images. You need data to compute it. So you can train a deep net that takes the prompt as input and it returns the conditional entropy curve as output, and probably you can train that deep net without spending too much. So it's really not unfeasible. So you can definitely do it. You don't want to compute it empirically. You want to have a deep net that does it for you. If you want, you can enforce monotonicity. It's a cool project. It depends how much it's worth it, depending how much there is variation, right? If the curves are very different depending on the prompt, it's worth. If those curves are almost the same depending on the prompt, it's not worth. So the starting point for a project like this is just try the prompts you like, just align the curves and see if they look the same, then it's probably not worth to pursue. If they look very different, yeah, there is grace that you can scrap from it. And it's interesting. It's something. If these curves are different, then it's a very feasible project.
But would you even start with the curves? Wouldn't you start with like an empirical study of the image statistics of different classes?
Or just you generate images and then you compute the entropy for those generated images. Okay. Or you don't even generate, you just look at the data sets. That's better. You just look at the data sets of prompted images, and then you just you compute the entropy, and then you look how much the entropy depends on the prompt. And based on that, you can see whether there is room for optimization. So the fact that often images look quite like each other from a statistics point of view, so I'm a bit skeptical that these curves will look that different unless you're talking about some of them will, right? If it's something like if your prompt is a grid, if your prompt has some clear frequency components, that it will, right? If you're prompting for something that is that has spectral peaks, it's just that on average people don't. These are not common prompts, and average scheduling will still do a good job there, you know. Yeah, so I mean it's about seeing. I honestly don't know. I mean, I can imagine that you, of course, if you ask for a city skyline or if you ask for like clouds in the sky, you can have a quite different entropy curves, especially something with very sharp edges, right? If you ask for a skyline with very sharp edges or something very smooth, that will probably change the entropy rate near zero significantly because it stresses high frequency significantly more. Yeah, so in that case, probably you get yeah, you can get an interesting effect there.
Okay. Hi. Yeah. So, any other questions?
I did have one. I guess it's kind of related to the class conditional stuff. Because I'm doing image conditional stuff, and I'm wondering if the theory kind of says so a very simple example is the SDE edit paper where they will add noise to an already existing image and then denoise, but from a not from the final time step. So you denoise the image from a partially noised image.
Mm.
Could you be able to infer then that you pick your the noising level based on some kind of entropy rate? I guess I'm having issue formulating it. I guess maybe picking it based on the spectral rescaled entropy, and then you kind of say, well, I kind of want these features to be prominent.
So I mean, in some sense, it could be like, okay, so regarding features,
I guess the question is more whether you can use, instead of asking what's the most accurate spectral weighting, would you be able to compose a scheduler that biases towards specific weights?
so I'm not sure because like there is a paper that specifically deals like with features, and then they said like there's like a phase transition where you start losing your like features where they like invert, like where local features actually start when you start adding noise, like local features start getting lost, so to say, while like global features are still there. But then after a certain point in time of your like noising process, they flip and like your global features just like plummet. They like the curve is almost like you cannot recover global features anymore, like they're gone. Like class would be one of those global features, like a class of your image, and then like local features would still be present in the image, just like I mean, still it will still be decreasing, but it will be present more than like global features. So I mean, I'm not sure, but like they showed it, but the thing is, you would probably have to like so they had toy example. They had like some theoretical example, and then based on that, they conjectured that happening, and then they tested it with adding noise and then comparing similarities between like different levels in some classifier, like CNN classifier of that data set, I think, or something like that. So they would look at like, and they said like, oh, first layer of CNN classifier actually looks at like local features, and then they would look like at similarity of like denoised image and like clean image, and then they would say like, oh, what is the similarity between those things, and then look at like deeper layers. And they said like the deeper you go, you're looking at more global features because it's a classifier. Like the last layer is class feature, which is the most global feature. And then they noticed the similar thing there as well, that actually you first start losing local features, and global feature is quite robust to first addition of noise. So probably you wouldn't want to lose your class feature, right? So you wouldn't want to go over that time where your like global features just disappear and your like local features are still there lingering but are really small. So I guess you don't want to cross that phase transition point.
Okay.
And how you find it, I mean, they just did like empirically. There is no, I don't think there is like a theoretical way because it depends on your data set and everything. Yeah.
Which paper was this?
Probing hierarchical structures of data. Probing. Yeah, theoretically, we'll see. Yeah. Yeah. So, or did I missed the paper? Okay, so the other paper, not the, like they have two similar papers, not this one but the other one. Yeah, so not this one but the other one. So I would have to a phase transition diffusion models reveals. Yeah, this one.
Okay, thank you.
Yeah. Yeah, so I can show you the. So you see, like they start with this image, they add a bit of noise, then they denoise it, and you can see as time increases, first like the local features change, like the I don't know, ears are a bit different, head is a bit different, like fur is a bit different, and then you just start increasing, like, and then at one point, actually, kind of local features are still there, like this whiteness and everything. I mean, local, and then like global feature, like class is totally different. It's not a cat, it's not a wolf, it's like a butterfly, and then they have like these curves, like cosine similarity between. Yeah, so you can see that depending on layer, like how it changes, and then you have like this inversion point where like your local features, like initial layers, are still there, and your global features, like your logits, are, I mean, completely disappear after this point. Yeah, so probably you would want to be like, you can look at this and then guess where you want to be. Like, you probably don't want to noise this much because then you're losing everything. Like you give house as an input and you want like different color of the house and you just get like a bus. Well, you would probably want something like here, yeah.
Okay. Thank you. Super interesting.